Pleasure being here in Florida. I would like to thank the organizers for organizing this very interesting conference. My first ILSI, definitely not the last one. My name is Arttu Luukanen, but you can pronounce it like R2 without D2. That's usually the easiest way of explaining it. And it's nice to be here in Florida, even though I have to say that it is colder than I have usually been here. So I think this is the first time I'm actually turning heating in the room on when I've been to Florida. So anyway. So I'm with a company called Solar Foods. We are based in near Helsinki, Finland. And we are quite literally liberating protein production. What does that mean in practice? Let me see if I can advance my slides. There we go. Okay, this is the disclosure slide where I have my first typo. Apologies for that. We have been funded on some of the topics here by the European Innovation Council, as well as the European Space Agency, which Sonia kindly mentioned in her speech. So we have been funded by the ESA Open Innovation Ideas platform. But obviously we have also lots of investors. We are a private company, so we have venture capital and also private investors, as well as actually the Finnish government is one of our shareholders. Right, so what is the premise of what we do? You have heard about microbial proteins, you have heard about cultivated meats, but one of the sort of really interesting things about the way we do this protein is that we have no connection to agriculture. What does it mean in practice? It means that there's no feedstock that goes into the manufacturing process that has an agricultural input. What in practice that could be is that if you do yeast-based protein production, you require sugar. As soon as you require sugar, then you need to have that sugarcane farm somewhere. And that drives up your land use and your water use for the food production. But what we do is that we have discovered from the Finnish countryside a hydrogen oxidizing bacterium that is new to science, and we have patented it. And it's special in the sense that indeed it doesn't use light like algae does, or it doesn't use the sugar like yeast do, but it uses hydrogen as its sort of gasoline to drive its metabolic machine. The source of carbon, because any organism requires that carbon so they can build itself, the source of carbon for Solein is CO2 gas. So the two main feedstocks for this food production is hydrogen and CO2. Let's look at some of the details in a little bit more clarity. So how do we get ourselves into these gases? So the CO2 we capture using direct air capture technology from the air, and we actually capture some humidity and water at that point. The hydrogen we get from electrolyzing water with green electricity into hydrogen and oxygen. It's not just air, okay, it's for full disclosure. We do feed it a growth media, which is water-based, and it has a pinch of minerals or salts, similar salts that plants take from the ground with their roots. And given that we're making ammonia, we do need a source of nitrogen. And that nitrogen for us is ammonia at the moment. The microbe actually has a ability to assimilate nitrogen directly from air, but right now we haven't optimized the process such that it could do that. Right now it's just easier to do it with ammonia. So we then provide the bacteria with these ideal conditions to grow, and it happens in a bioreactor, a gas fermenting bioreactor, and it starts fulfilling its purpose in life, which is to multiply. And this is a continuous process, so once the biomass density has increased enough, we can start harvesting the biomass out. Actually, almost all of the water is recycled. We use basically dairy industry separators, and then a spray drying system to dry it into a dry powder. So the net water usage is actually very low. So yeah, the end result is this sort of orangish dry powder. The orange color is kind of interesting because it is actually due to the fact that it's very rich on beta-carotene, and that's where the color comes from. The nutritional profile is quite attractive. It is up to 70% protein, with some dietary fibers, some fats, and minerals. And the idea is to use this as a food ingredient to replace your animal or maybe even plant-based proteins. But you all know, especially at this conference, better than I do, not all proteins are created equal. And the value of the protein is really much dependent on its amino acidic composition. So Solein quite nicely has this complete protein feature. So we can provide all of the so-called 9 essential amino acids that our bodies don't metabolize and are pretty strong with others. It's actually kind of in head-to-head comparison, very close to dried beef from the standpoint of the amino acid composition. Fares well in comparison to many of the other alternative proteins or plant-based proteins, with the fact that we can also provide ample amounts of B12 and B vitamins. Also, there's lots of iron and the carotenoids, which I already mentioned. But obviously, the mission that we're on here is really to reduce the environmental footprint that protein production currently has on our planet. And if you compare solein production with respect to its greenhouse gas emissions or freshwater withdrawals or the land use, these are small fractions in comparison to either the animal or also plant-based proteins. The land use is interesting because the land use is really, truly the footprint of the factory, and I think in this calculation we also had the solar panel farm with the wattage that we need for it. Right. So, okay, so the powder itself is obviously gets a bit boring if you just eat that. So we actually have a food team at Solar Foods who are developing applications, in other words, recipes, where we utilize solein as the protein ingredient. So this is a salad where we made this sort of a chicken meat-like imitant. That can be produced by doing heat extrusion and adding some oil to it. And you get this quite nice texture. One of the things and superpowers of solein is that this is an ice cream that we had on market in Singapore at our partner restaurant. We launched in Singapore in the September of 2022 in conjunction with our novel food approval in Singapore. So it works well in ice creams. And one of the superpowers of solein is the fact that its self-taste is sort of an umami-like. So it's a very mild, mellow taste of its own, and umami is quite nice, as you well know. It's sort of a food taste fortifier. And that's really the taste of protein, per se. Pasta is also works well, so here there's no egg, it's just all solein. And then we have made all these pictures you see are actually pictures from the food team of the things that we've done and developed. Actually, when the Deep Space Food Challenge judges visit us in Finland, we served a protein shake, so water, solein powder, and a few berries in there, and voila, you have your space shake. So this was one of the, so for any alternative protein company, there are sort of three major milestones that your company has to pass, otherwise you'll die. The first one is that you discover an organism that produces protein that doesn't taste terrible, it tastes good, and it works well with recipes, so it forms structure. The second one is that it's not dangerous, you don't get sick if you eat it, and it has a good nutritional profile. And then the third one is the scaling. So the first two I've just gone through here. So now we are on milestone number 2, which is that we have our first regulatory approval. We expect to get the US FDA self-GRAS here in US by the end of this year. And the EU, for being so quick, it's going to be 2025, so next year. Even though we filed at the same time as we did for Singapore. Well, that's EU for you, unfortunately. So here are just some pictures of the menu that we served when we launched in Singapore. So we had it wasn't we're not serving solein-based foods there constantly because we are, after all, at the moment, and coming to the scaling thing, we are running a 200-liter bioreactor that produces 10 kilograms of protein per week. So we don't have a lot of stuff at this point when we launched this. So we had this one event, and invited a fair bit of people there and got some nice press coverage. And all the dishes that you see here have replaced the protein with solein in various quantities. We also, of course, are very much talking to food manufacturers. So we announced together with Ajinomoto that we will be develop products using solein and conduct test marketing in Singapore in the first half of this year. So this activity is already ongoing. And there are other companies that we are also talking with. I want to shift gears just a little bit before I go to the scaling part, which is that we do heavily invest in R&D. Just about 6 months ago, we received a relatively sizable grant from the European Innovation Council on a project that we call HydroCow. Probably get the idea where we're going. So here we will actually genetically modify solein for protein secretion machinery. In other words, the protein, as it is currently, is the cell mass. It's from the cell mass itself. But with this project, we hope to engineer the organism with an ability to secrete protein. And this is very, very exciting. We have quite a nice consortium, four partners, including us. We have the Technical University of Aachen, who are bioinformatics experts. They will basically, based on our genome data, work out the intricacies of how that bacterium works. Then we have the University of Groningen in the Netherlands. These are genetic modification experts. They will modify the genome of the microbe such that, based on the Aachen data, well, how do we need to modify it for it to have an ability to secrete protein? And then we have FGen, which is a part of Ginkgo Bioworks in Switzerland. They have this incredible ultra-high throughput screening platform where they can screen 1 million strains a day for protein secretion. So we will select then the best strains, and we will validate those strains in our R&D reactors at Solar Foods. But what really makes this so interesting, and we have selected as the pilot protein for this project, we've selected beta-lactoglobulin, which is one of the milk proteins, because we think it may be easier than maybe some others at this early phase. But if we get this beta-lactoglobulin business working, it could be a whole new field that opens up, that we use the cell as a factory to manufacture other things. So we could go into other food proteins, maybe we could go to materials and pharmaceuticals, using hydrogen oxidizing bacteria with this minimal environmental footprint. So very exciting days. But we are early on the project, it's just started, so no results yet, but keep posted. I'll keep you posted. We've also been quite substantially, and there was a panel earlier today where it was the correct notion was said that this is infrastructure that is expensive, and for a startup to afford to build a factory, it's a big ask. It's a big ask to your investors to say that, yeah, we know we can do this, but do you trust us? Can you give us 100 million that we build our first factory without any revenue? Not many investors are going to give you 100 million. So the EU fortunately did. So we have received the largest food grant ever in the world under this IPK, Important Projects of Common European Interest, which is 110 million in total. We've received the 34 million as the first tranche, which is going towards the first factory that we've just been completing. So now we're getting to the scaling challenge. So 34 million is going to go to ramp up of the factory. We get the process running, get the product out of the pipe, and the remaining 70 million is going to go towards the next factory, which we plan to be a factor of 100 larger than this first factory. So the first factory is 100 tons per year. The next one is going to be 10,000 tons per year. This is a sneak peek from the factory. So it very much looks like a brewery, like somebody said. Lots of piping, lots of tanks, lots of analytics, CO2. This is the CO2 capturing system. We actually have the CO2 direct air capture system hooked up into our air conditioning system, so all of the CO2 that our staff puts out or our visitors is going to be turned into food in the factory. Price, consumer-wise, obviously, a key metric. It is right now quite expensive because we're producing so little. It's going to be still quite expensive with our first factory, so it's going to be sort of 30 euros per kilo. But once we get to the factory 02, which is the 10,000 tons, we believe that we can meet whey, pea, and soy protein price point. So it's not going to be a premium protein, despite the fact that its nutritional profile is superb. All right. That's a story here on Earth. Let's launch us to space, where I'm leading our space activities, and I'll try to justify why we do that. So you've heard about DSFC, the Deep Space Food Challenge. We've been also, like Interstellar Labs, in it and won the phase 1 and 2, and now we're executing phase 3. And we've done some work towards this already, even though there's not a single dollar of prize money in it for us because we are a European international contestant. But we do it because we can. And we have, during the challenge, we have designed kind of a conceptual design of a spacefaring bioreactor, which is obviously much, much smaller than our factory, because we only need to feed maybe 7 astronauts, something like that. So sort of 50-liter hydraulic volume scale. But there's one thing here which is actually pretty fascinating. Okay, so we use hydrogen and CO2 as the main feedstocks. So this is a picture of a space station, what's called an ILSI, Environmental Control and Life Support System. So if you go online and you learn about these things, you will learn that 90% of the water that the crew uses for drinking and food rehydration and washing is being recycled. The ILSI also removes the CO2 that the crew puts out. But actually, there's a net loss of water, which has to do with oxygen generation on board the space station. So water is being electrolyzed into oxygen for the crew to stay alive, and hydrogen. But the hydrogen currently goes out of the window. It goes to space. It's not used. It's a waste. But if I split a liter of water into H2 and O2, and I throw away my H2, that liter of water is gone. It's gone for good, because you cannot burn those molecules back to water anymore. For this reason, the ISS loses, it's about a half a liter per crew member per day. The ISS loses about 1,200 kilos of water per year. If we are going to Mars, crew of 5, 3 years, 3 tons of water, which is a large mass to launch. So our sort of concept here for the Deep Space Food Challenge is that we close the O2 and the H2 loop here. So the hydrogen, we can feed all of that excess hydrogen. If we repipe the ILSI, we pipe that hydrogen into the reactor, and the bacteria can eat all of that CO2 that the crew is putting out. So this saves all of that water that would have been otherwise lost. And especially the further you go, the more you save. There are some other interesting things here. So the energy use is actually 85% of the energy that we use is the hydrogen production. But given that we don't have to do the hydrogen anymore, the energy and power requirements are very, very low. We just need to run a few pumps and a PC and some valves and maybe some instrumentation. So very low. We are also thinking about how do we close the nutrient loop, because I did mention that we do feed a growth media with some minerals. You could, in principle, recover those minerals from feces if you just have a method to do that. And I don't personally want to get into that. It's somebody else's problem, but you could, in principle, do that. Actually, even if we don't, the mineral weight is only 5% of dry mass, which for a 3-year mission to Mars is going to be like 75 kilos. So it's not a big deal. But it would be nice to close that loop, just for completeness. What is the value proposition here? So we actually are looking at this as a potential business for the company. Not on Mars or the Moon maybe, but maybe Leo, because the next generation of space stations that will be launched from, I think, next year onwards, those will be private space habitats, operated by private companies, and the main tenants being the agencies. And if we can save a habitat, 1,200 kilos, or maybe, and it depends on the occupancy, it could be much larger, we can save tons of upmass, so that you don't need to resupply those. The other thing which is a value proposition for, especially when you go to the Moon or to the Mars, is that if you don't need to fill your cargo mission space with consumables, water and food, sausages, steaks, you may have space for another rover, science equipment, telescope, something that has a massive value for the mission, for the stuff that we can save. But we, as a company, obviously, for us, most important thing that for this to be sustainable, it needs to be sustainable also from a business sense. And that's kind of where this plot comes in. So current launch cost to LEO, with SpaceX Falcon 9, Crew or Cargo Dragon, we're talking about $50,000 per kilogram. So for that ISS case of 1,200 kilos of water saved and food produced. And actually, interestingly, you see that most of the savings comes from the water savings. The food mass is kind of a fraction of it. So we could save a private space habitat $40 million per year, which to me suggests that we could maybe charge them $20 million a year for a license fee to run the bioprocess there, and they would still save half their money. Right, I am coming to my end. These are my key takeaways. I'm here the whole evening. Love to talk to you, and thank you for your attention.